Okay, as promised in the last lecture, we begin today with Newton's laws of motion. These were devised by Isaac Newton, later Sir Isaac Newton, in 1687. So they're, by my math, that makes them 333 years old today. Well, not today, but this year anyway. So these are pretty impressive accomplishments for something that occurred so long ago, and with the very limited technology that was available at the time. Newton based his work on previous work by Galileo, and Newton basically took it several steps further, and Newton's laws were considered sort of the be-all and end-all of motion. Basically anything in motion was considered to obey Newton's laws until the early 20th century, when quantum mechanics was developed. Because it was found that subatomic particles like protons and neutrons and electrons don't obey Newton's laws. But basically, you have to get down to that really tiny level before Newton's laws don't apply anymore. So again, pretty impressive accomplishment. We begin with Newton's first law of motion. And that one is also known as the law of inertia. And it says that an object at rest will tend to remain at rest, and an object in motion will tend to remain in motion. At the same speed and in the same direction, unless acted upon by an unbalanced force. And remember what we said about acceleration. We define acceleration as a change in motion. And it can be a change in speed, or it could be a change in direction. So if something is sitting still and it starts moving, that's a change in speed. That would be an acceleration. If something is in motion and it slows up or speeds up or slows down, that would be a change in motion, so that would be an acceleration. If something is in motion and it changes directions, that would also be an acceleration. So another way of thinking about this would be that acceleration only occurs if there is an unbalanced force. But we're getting ahead of ourselves a little bit, because this is actually coming very close to a statement of Newton's second law. So actually, it turns out that Newton's laws of motion are related to each other. So we'll come back to that when we talk about the second law. Now, it's important to remember that Newton was talking about idealized situation in which there's no friction or air resistance to the motion. And that's not, that's quite different from the situations that we face in everyday life. So an object that's in motion in everyday life will tend to slow down over time, just because of either friction or air resistance. And actually, technically, in Newtonian terms, friction or air resistance in those cases would qualify as unbalanced forces. But in the absence of those particular unbalanced forces of friction or air resistance, an object wouldn't require any applied force to keep moving. So we're talking about situations like in outer space where there's no because there's no atmosphere out there, there's no wind resistance, and there's no gravity, and there's no friction. And so once an object starts moving, it will keep moving at that speed basically forever until, until it hits a planet or something. Okay. But in that case, you might wonder, what maintains the motion? What keeps the object moving? And the answer is inertia. Inertia is, well, it's pretty much what we've just described here. Inertia is a quality that tends, inertia is a quality that anything with mass has, and it tends to resist changes in motion. And so inertia is possessed by everything that has mass. So all matter has this property. And it basically is a property that resists changes in motion. And because of this, as I said, Newton's first law is also known as the law of inertia. Inertia is determined by an object's mass. The greater the mass of an object, the more inertia it has. Okay, so larger objects have more inertia. That makes sense, because if you think of just trying to get something moving, if you have, if you're trying, if you have like a child's little red wagon and you give it a push, it starts moving really easily. On the other hand, if you have a car and you give it a push, it's not going to start moving really easily because it's got a lot more mass. And by the way, did you check to make sure that it's not in park? Okay, so assuming it's in drive and you give it a push, it's not going to start moving unless the engine's running, because it has a lot more mass, and therefore it takes a lot more force, or therefore it has a lot more inertia, and it takes a lot more force to get it moving. Okay. So, moving on to Newton's second law of motion. Number 2. And this says that acceleration of an object is directly proportional to the net force acting on the object. Okay, so the acceleration of an object is directly proportional to the net force on the object. Another way of saying that would be, mathematically, A alpha, remember the Greek letter alpha means proportional to F net. And that's assuming that the mass of the object is remaining constant. So what that means is if you double the force, you double the acceleration, as long as the mass doesn't change. Okay, Newton's second law also says that the acceleration is inversely proportional to the mass of the object. Okay, another way of saying that would be A is proportional to 1 over m, and that's assuming that you're applying the same force in each case. So if you apply a certain force to or a certain amount of force to one object, you get a certain acceleration. If you apply that same force to an object with twice as much mass, you'd only get half as much acceleration. So that's what inversely proportional means. Okay, and basically this tells us this is basically what happens when an unbalanced force is applied. Applied to an object. The equation may look a bit familiar because it's F equals ma. So we kind of already saw that. And you can rearrange this equation to find mass or acceleration. Acceleration would be F net over mass. And in terms of the SI units, mass, of course, is in kilograms. Acceleration would be in meters per second squared. And so force would be kilogram meters per second squared, which is where we get the Newton from. Okay, so we have our, remember we can also, since this is a three-term equation, we can also use our triangle to arrange it. It's MA, so M and A go next to each other on the bottom, and that leaves F to be on top. So again, if we want acceleration, we cover that up, and that's F over M. If we want mass, we cover that up, and it's F over A. And so now we can easily find any of those terms. Looking at the original equation, we can also see that, yes, it makes sense that force would be proportional to mass if acceleration is the same. Force would be proportional to acceleration if the mass doesn't change, and that if the force stays the same, then mass would be inversely proportional to acceleration, because when you have to multiply one thing times another to reach the same goal, then basically as one of the things you're multiplying gets bigger, the thing you're multiplying it by has to get smaller by the same factor if the result is going to remain the same. Okay, so if you want the force to come out the same and you double the mass, you have to cut the acceleration in half. And vice versa. Okay, so that's things you can do with that equation. I have some, okay. Okay, and remember also that there's an analogous equation for weight, because weight is a force. It's a downward force caused by the pull of gravity on your mass. And so the units for weight in the SI system would be the same as the units for force, which would be newtons. And the SI units for mass, of course, are kilograms. And remember that G stands for gravity, which is a form of acceleration. And the units in the SI system would be meters per second squared. Okay, so some examples that you could work with these questions or with these concepts. So suppose you have a 6,000 kilogram truck and force is applied to it and it ends up accelerating at 2.2 meters per second squared. And this is on a level road, so we don't have to worry about gravity being involved or anything like that, because that would make the problem quite a bit more complicated. And so, ignoring friction, which is the kind of thing that we often do in physics in order to simplify things, we have F net equals ma. Mass and acceleration were already given in the standard SI units, so you don't have to change them. The mass is just 6,000 kilograms, and the acceleration is 2.2 meters per second squared. And when you multiply that out, you get 13,200 kilogram meters per second squared. Which is 13,200 newtons. And in terms of significant figures, 13,200 is actually 3 significant figures. If there's no decimal point, the zeros at the end don't count. But the numbers we put in, 6,000 with a decimal point is 4 significant figures, but 2.2 is only 2 significant figures. So our answer should be in 2 significant figures. And 13,200 rounds off to 13,000 if you need it to be two significant figures. Okay, so that would be kind of an example of what you can do. So say, on the other hand, a force of, say, 500 newtons is applied to a box with a mass of, 10 kilograms, we'll say. On a frictionless surface, what should be its acceleration? All right, well, we saw up above here, acceleration is just force divided by mass. We've already got SI units for the force and the mass. So we have 500 newtons divided by 10 kilograms, and that would be 50. Newtons divided by kilograms would be meters per second squared. Okay, so that's pretty fast acceleration. About 500 newtons is quite a bit of force to put on a box that only weighs 10 kilograms. Normally, you wouldn't get acceleration anywhere near that because of friction. But like I said, in ideal situations like this, we often ignore things like friction. An example with weight could be how much would an 80 kilogram person weigh in several different places? First of all, on Mars, where the gravity, acceleration due to gravity is 3.93 meters per second squared. And B, on Earth. And C, on the moon, our moon that is. And the gravity on the moon is 1.63, oops, sorry, not times, it's just 1.63 meters per second squared. Okay, so A, on Mars, weight, again, is just mass times gravity. And as long as you have compatible units, SI units, then you can just multiply them. Kilograms is the SI unit for mass, so we can use that as it is. And we need acceleration due to gravity, which on Mars is 3.93 meters per second squared. And if we do that, we get 314.4 newtons. But we need three significant figures, so I'm going to call that 314. 314 newtons. B was on Earth. Actually, on Earth, there are a couple different ways you could do this. First of all, using weight equals mass times gravity. It would just be 80 kilograms times 9.81 meters per second squared, which is the acceleration due to gravity on Earth. And we get 784 newtons out of that. And oh, sorry, this is basically the only way we can do it with the information we have. I was thinking of going from pounds to kilograms. Going from kilograms to Newton, that's pretty much the only way to do it. C would be on Earth's moon. Weight is, again, mass, 80 kilograms, times 1.63 meters per second squared. And that would land us with 130 newtons. Okay, so 130 newtons would be the mass for on the moon. Okay, let's weed through. I got some notes here for some stuff that's not really relevant to this part, so we can move on a little bit, and we get to Newton's third law of motion. So Newton's third law of motion Newton's third law of motion is whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. That's the formalized statement of it, and I'll write that down now. Okay, opposite direction to the force exerted on the other object. All right, so when two objects interact, the force exerted on one of the objects is equal in size and opposite in direction to the force exerted on the other object. Well, another aspect of this is that what that means is forces always come in pairs. Because if you exert a force on, say, the little red wagon, you're giving a push. It may not feel like it, but the wagon is actually pushing back on you too. And so that's the pair of forces that are working in this instance. The best known statement of the law is for every action there is an equal and opposite reaction. And that is a less specific way of saying it, but it is also true. So for every action, there's an equal and opposite reaction. Newton's third law. Okay, we're at about 30 minutes now, so I'm going to cut there for the first segment. and we'll come back in a moment for the second.